Yes, I'm Kevin Weatherill. I'm from the physics department at Durham University, which is part of the Joint Quantum Centre, which also includes Newcastle University. And in Durham, we have a small centre where me and my colleagues, Charles Adams and Matt Jones, study Rydberg systems, atomic, molecular, and solid state. So I just want to tell you a bit about some of the recent experiments that we've done. Okay, so I'll begin by introducing those who aren't familiar to the concept of Rydberg atoms and explain what their properties are and how those properties lend themselves to being useful for quantum technologies and even quantum information technologies. I'll then tell you about two recent experiments that we've done. The first being using thermal atoms to do terahertz imaging with Rydberg atoms. And then lastly, looking at the cold atomic samples are used to collectively encode single photon qubits and indeed Q-trits. So what do I mean by Rydberg atoms? So we're talking about atoms that are highly excited. So atoms that have been promoted to a state with a high principal quantum number. So we are used to mostly dealing with ground state atoms, which is where nature gives us them, and they're angstrom scale units. But when we excite up to some high-lying state, it's still an atom. It still has well-defined quantum numbers and all the rest, but now it can have a very extended electron wave function. And we can deal with atoms up to really quite macroscopic sizes of microns. And this leads to some quite exaggerated properties of these atoms. So the size of the atom scales with the principal quantum number squared, which means that the dipole moment of the atom also scales in this way. And the effect is that as we go up the ladder here to higher lying states, that the electric dipole transitions become stronger as we go up to higher principal quantum numbers. These atoms are quite long-lived, so the lifetime scales with the third power of the principal quantum number, which means even for quite low angular momentum states, the atoms will hang around for quite a long time. So we're talking at least microseconds here, so there's time enough to do different operations on them. The sort of delocalized electron leads to a high polarizability, so that scales with the seventh power of the principal quantum number, and means that we end up with an atom that's very sensitive to electric fields, and so for this reason, Rydberg atoms are used for sensitive electrometry. But probably the most relevant here, and actually the most impressive, is this 10 to the power 11 scaling of the van der Waals interaction. So the atom-atom interactions. These atoms have very strong and long-range interactions, which makes them useful for numerous applications. If we take a look more generally at the atomic structure, what's nice about atoms is they allow you to span large regions of the electromagnetic spectrum. So I've chosen an example here of the cesium atom, and actually cesium has quite a low ionization energy. But even so, if we want to excite a cesium atom from its ground state up to a Rydberg state, we need a photon in the ultraviolet. More typically in experiments, we might use a combination of infrared and visible lasers to do stepwise excitation up to these Rydberg states. And once we're up in the Rydberg manifold, then there are a whole host of transitions that span the terahertz, microwave, and RF field. And these are very strong electric dipole transitions, which is the reason why, again, these Rydberg atoms are finding increasing use as sensitive microwave and RF detectors and are being used for sensitive communications applications. The next thing I want to talk about is the idea of the Rydberg blockade. So this is using the idea of the strong van der Waals interaction. And this is what's most pertinent really for the quantum information type applications. So if we consider two atoms shown here that are separated by some distance r, if that r is sufficiently large and in particular greater than a characteristic distance known as the blockade radius, which we call RB here, then when we try and excite these atoms, we can excite the first atom to a Rydberg state, and then we can excite the next, and there's no problem. We can just excite all the atoms. When the atom samples become more dense, or in this case, our two individual atoms are moved close together, then there is a shift in the pair state energy, which means that we can no longer excite more than one atom. So we can excite the first atom, but then we can not excite the second atom because the pair state energy has been shifted out of resonance with the driving field. So this means we can excite one and only one atom in this ensemble. So this is known as the Rydberg blockade. And not only can we only excite one, but we can't know which atom it is. So we have this kind of entangled state. Because the blockade radius can be macroscopic in size, it can encompass entire ensembles of atoms, so we can have many thousands of atoms within a blockade radius. This means that we can get these kind of macroscopic entangled state situations. And so this has been used to study interesting phase dynamics, for example, in many-body physics. There are applications in quantum computing that I'll mention a little bit more in the next slide. And the things that are most of interest to me and my colleagues in Durham, which is the quantum optics, so how the photons that are interacting with these atoms themselves behave. So just before I move on to tell you about the experiments that we've done, this is a cover from a Physics World article from 5 years ago now, where they were discussing the rise of Rydberg physics. So that they recognized that Rydberg atoms offer this really nice platform where we can have individually trapped and addressable atoms that are interacting over length scales that are much larger than those on which they are trapped or excited themselves. And so this means that you can make large scale and scalable quantum simulators and computers using this type of system. So I went looking for quite recent examples of different technologies. So I found 2 papers from this year, one using superconducting qubits. Now, atomic systems have a way to go to catch up on the fidelities and speeds of these kind of operations. But one thing that the atoms really do have is this scalable property. You can make, using optical lattices and optical tweezer arrays, you can make these large scale and scalable arrays of quantum bits. So I highlight a paper here from Misha Lukin's group in Harvard, but there's notable work as well from the group of Antoine Brares at the Institut Optique in Palaiseau. And there are groups such as John Pritchard's and Strathclyde who are setting up this type of experiment, and indeed companies cropping up trying to make this kind of device. Okay, so I'll quickly tell you about 2 experiments that we've done recently in Durham. The first of which isn't terribly quantum, but actually it's quantum inspired, I would argue, and is quite exciting from a technological standpoint, and that is using Rydberg atoms for terahertz imaging. So the idea is actually very basic. We have some sample of Rydberg atoms, and we use these atoms to convert a terahertz field into an optical field. So because the atoms have already been pre-pumped by lasers, then we can use just a simple trick of electric dipole selection rules in the atoms to help us convert a low energy photon, essentially with quite high efficiency, into an optical photon that has 1,000 times more energy, which means that it can then be detected on a standard optical camera. So terahertz detectors generally have difficulties working, certainly at room temperature, because of the low photon energy. So this is quite exciting for us. This gives you an idea. So this is just a calculation of where we expect transitions within our atoms to be and at what frequency. So we can pick and choose which frequency we want to operate at and use our atomic sample to do this conversion and help us do some imaging. So this video, if it will play, and if it transmits across the interweb, shows a slowed down sort of high-speed video of a water drop. So this is a water drop falling from a burette, and it's imaged at 1,000 frames per second, but played back at 30. Now, this might seem unremarkable until you realize that there is about 2.5 centimeters worth of optically opaque plastic screen in between the water drop and the camera that's taking the images. So what we're doing here is the terahertz is penetrating the screen but it's quite strongly absorbed by the water. So we're getting a kind of absorption image, but transmitting through a thick screen. And this works actually through plasterboards. So we can argue here that we can really, we can do high-speed imaging through walls. So if you want to read more about this, it's in this paper from last year in PRX. And just to compare with the state of the art, you can see here, I haven't really got time to explain any of these other devices, but you can see that Rydberg atoms are really in a class of their own when you look at the sensitivity and frame rate of a full field 2D kind of focal plane array type imager. So we're really excited about this, and developments are ongoing to push this as a technology. Okay, so in the last little while, I want to tell you about another experiment. So this time, instead of using thermal vapors, we use cold atoms. And I should really point out this experiment has been a long-standing experiment led by my colleague and collaborator, Charles Adams. And here we are storing and manipulating photons in cold atom samples. So the idea that's behind all of this is that of the dark state Polariton. So introduced in this paper by Fleischer and Lukin more than 20 years ago now. So the idea is this: if we have our atom and we are going to probe it with an infrared photon here from this transition from the ground state G to some excited state E. And then this is a weak probe field. It's then the atom can be coupled up to this Rydberg state using a strong coupling field. So on resonance, there's a eigenstate that's a dark state. So this is known as a dark state. And then if we can dynamically reduce the intensity of this field, then we can map this probe field into an excitation in the medium. So this is the idea of a dark state polariton, and it's the idea behind many quantum memory devices. Well, what's key about using Rydberg atoms with this kind of scheme is that we have this additional blockade effect, which means that if all of our atoms are within a blockade radius, we only excite one atom, which means that we only store one photon. And then sometime later, so after we've reduced our coupling, the group velocities approach zero, the optical field is stored in the medium. We can then dynamically ramp up the field, and that means that the stored photon is read out, hopefully into the same spatial mode that it went in, and we can detect that. So here's some data I'm going to show you from the group of Treporto and JQI. I show this because it's better than ours, because they have a higher optical depth and more laser power. But just to show you that this really results in a very good single photon source. This is their G2 measurement, and their coincidences are suppressed really strongly. Another thing that's interesting about this sort of scheme is because the interactions between these Rydberg atoms can be so large, we can actually make single photons interact over macroscopic distances. So this is a result that we showed some years ago. So for the purposes of this talk, we're going to talk about collectively encoded qubits. So the idea is we can store a single photon in a Rydberg state, but this excitation is stored amongst the entire ensemble of n atoms. So we're going to have this type of state here, and we're going to call that zero for the zero in our kind of qubit basis. We can then come along with a microwave field, and we can couple this first Rydberg state to a second Rydberg state R primed, and call this state 1. So this is another collective state where now all of the atoms are in the ground state, barring one, which is in R prime. And so we can dynamically cycle between these states. So one could pitch this as a collectively encoded qubit. But one thing that it has potentially an advantage to other collective encoding schemes is that the Rabi frequency now between these two qubit states is not dependent upon n, the number of atoms. So if we repeat the experiment and n changes, it doesn't matter so much because the Rabi frequency stays the same. So if we repeat this experiment many, many times, and vary the time that we detect the photons, what we can see is some quite nice Rabi oscillations that persist for some time. And we also observe that these dynamics are robust to atom losses and electric field noise, and we can do things like Ramsey interferometry and other type of coherent dynamics. So if you want to read more about that, then I recommend this paper that's still on the archive, but should be published quite soon. Finally, just in the last couple of minutes, I want to take this idea just a little bit further, that we don't need to limit ourselves to storing our photon in one or two states. We can expand the state space. So if we imagine a situation where we come along and we store our photon initially in this blue state, and then we can apply a microwave field that can couple to this yellow state, we could then apply a different microwave frequency and couple to another nearby Rydberg state and start sharing the excitation around in that way. So if, for example, we wanted to create a state of this form, where we've got 1 over root 2, 0, which is our blue state, plus 1 over root 2, 1 plus 2, which is our yellow and green states, then if we, once we've stored our photon, we apply a pi by 2 pulse, on this transition, we would expect to have half the population in blue and half in yellow. And then we apply another pi by 2 pulse on the other transition, then we would expect to have 25% in the yellow and 25% in the green. And in fact, in our experiments, if we do this, we turn on our coupling field to read out the state, and we retrieve and time bin after each of these different operations, then we can see that indeed we can create this state and read out 50% in state 0 and 25 in 1 and 2. So this, we don't know particularly what it might be useful for yet, but it's just an interesting idea that we don't have to limit ourselves to a qubit. We can go to larger state spaces. So I'm running out of time, so I'd better thank the people involved. So in particular, I need to thank Charles Adams, who's really the lead on this cold atom experiment I just talked about. This is the terahertz imaging team and the Rydberg photonics team, and I should also thank our funders, and thank you for your attention as well. Thanks very much.